So can everybody see the slides? Does the transition look okay?
Yeah.
Okay, fabulous. First, we have extended our homework to today, and because I heard of some complaint about running um, the bagging and random forest to get all the results, and can take too much time. So I think 2 days more should be sufficient for you to get results. But also, we in the Piazza post, we provided some suggestion to improve the running efficiency of your code. So basically, try to avoid uh, the for loop as much as possible. Like when you compute the gradient vectors, compute the information in all kinds of stuff, try to do it using matrices and vectors, typically with Python NumPy and scipy library if you're using Python. Don't try to going from for loop and enumerate element by element. That'll be too slow. Right? And by the way, so don't feel scared that you're gonna run a few hours, uh, even one day to get the results. It is extremely common in machine learning applications. For example, in my group, we have a paper submitted to a top machine learning venue recently. Um, we just run those experiments. Like we purchased some GPU server, right? It just costs the fees per minute, right? We spent like more than 1 week to collect all the results. We spent like uh, $2,000. So it's really common that your program takes a long time to collect the results. But meanwhile, you need to really pay attention to your implementation. Don't try to use efficient approaches, especially take advantage of the numerical libraries, linear algebra libraries. Don't use the for loop. Okay. And the second thing is that you may have noticed that our homework 3 has been released, right? And I believe the programming part uh, in homework 3 is even lighter. Right? You are only required to implement the perceptron and the variance, and the data set is small, and running perceptron won't does not like running baggy trees for 100 iterations, right? So it will be much faster. So we set the number set to 2 weeks as our window to finish the work, and it should be more than sufficient. Right? And but again, I mean, you can't say, okay, I want to finish it like 1 day before the deadline, and then whatever problems in your hand, you won't have sufficient time to finish. So again, I will highly suggest everybody to start early, and so that we don't feel you don't feel like anxious, if you don't feel angry when you reach the end of the deadline. Okay. Uh, the third thing I want to mention is that because we haven't finished the part half of this class, um, we really want to collect your feedback. And we just give 3 survey questions listed on the canvas. If you are available, feel free to complain. Feel free to give extra comments. But by the way, don't complain the workload is too heavy. This is a problem I have emphasized at the very beginning. So we'll try to collect, we'll try to extract those really important and useful suggestions for you and to help you and to improve our class. We want to make sure that at the end of this semester, you do feel that you learn something real about machine learning rather than just, okay, give some grade A and pass through some course content and heard some concepts. That's not the goal of this course. And someone asked me that because this survey is anonymous, right? How do you get the bonus points? Actually, I have explained in a post, right? So once you finish the submission, right, you just take a snapshot of your submission page. That won't reveal your identity. and won't reveal what is your opinions on this course. You just send this page to our TM and tell us your UID, your name. Our TMs will record, will make a record that you have finished the survey, and you get 3 bonus points, and will be finally integrated into the final grade. Okay, so any question regarding the 3 things I just mentioned? Looks everybody is happy. Okay, so in the last lecture we have finished. We have wrap up the perception, right? The perception is our first learning algorithm about linear classifiers. And as we mentioned, we're going to look at a few different learning algorithms for linear classifiers, because linear classifiers are so important, so fundamental, right? It's kind of like a cornerstone, is a base from which we can extend to highly complex nonlinear classifiers. We'll discuss about it later, right? So next, we're going to look at another learning algorithm for linear classifier, namely maximum margin classifiers learning, or support vector machines, right? But before we introduce what is support vector machines, right? What can we learn support vector machine? We need to introduce a bit more concept in computational learning theory, and some kind of more advanced concept which can measure the complexity of the hypothesis space, right? It's called VC dimension. Don't worry, we're not gonna go very in-depth about the theory. This is not a theoretical course, but we do want to introduce you a few key concepts in computational learning theory, which are necessary, but sufficient for you to understand those advanced learning algorithms. That is the agnostic learning and VC dimension. So this lecture is not only in this lecture. I mean, this topic we're gonna discuss 2 things, right? First, what is the definition of the agnostic learning, right? So in our previous discussion in computational learning theory, right, we assume that, okay, you have a powerful learning algorithm and hypothesis space in which whatever data set you give, we're going to return a hypothesis which can fully correctly predict every training example. This is called consistent learning, right? We assume our learned hypothesis always have 0 training error. And then based on that assumption, we derive some sample complexity bound, right? If you want to reach a particular level of the true error or the generalization error under some particular level of certainty, and how many training examples at least you need, right? So that's called sample complexity bound, right? But obviously, this consistent learning setting is kind of like too strong, right? How can you guarantee that your training algorithm will always give a hypothesis with 0 training error, right? In practice, in many cases, in many practical applications, that won't be satisfied, right? So today we're going to talk about another much more realistic setting. It's called agnostic learning. So the key setting of the agnostic learning is that we do not guarantee a 0 training error anymore. And then we have to deal with a non-zero training error. And then a question regarding agnostic learning will be like, can we still get some estimate or get some bound about the true error or the generalization error? Right? You see that, yes, we can do that. And also we have some very elegant structure, has same kind of reflections on the sample complexity of consistent learning. And then we're going to introduce a very important concept. It's called shattering Vc dimension. So Vc dimension is defined based on the shattering behavior, right? So the Vc dimension was proposed to address a problem that, as we actually have discussed before, right? Previously, we used the size of a hypothesis space to indicate the complexity of a hypothesis space, right? The larger the space, the more complex your hypothesis space. That means you need more training examples to achieve the same error level on the same certainty, right? On same confidence, right? That also justifies the Occam's razor principle. But here, we'll see that in many machine learning models, right, the hypothesis space actually is infinite. That means when we substitute the size of hypothesis space, right, into the sample complexity bound, you simply get the lower bound of the samples are just infinite, right? That's not meaningful, right? So a natural question or critical question would be like, how can we give a finite measure of the complexity of a hypothesis space, even your hypothesis space is infinite? Right? That's how this Vc dimension was motivated and invented. Before we proceed, right, let us just briefly review what we have previously discussed, right, about computational learning theory, right? We introduced the concept about pack learning and Occam's razor's principle, right? So what is pack learning? The key idea of pack learning is that, I mean, in learning behaviors, right, we can never claim that our algorithm will 100% sure to get some particular level of accuracy in predicting future examples, right? Why? Could somebody recall why we can now say, okay, my algorithm is so powerful that in any case, it can give you 99% accuracy?
Because it's dependent on the training set size.
Yes, exactly, right? So no matter how powerful your algorithm, if your training set is is junk, is very bad, you won't be able to get good performance, right? And the training set are randomly sampled from some unknown data distribution, right? So obviously, you cannot guarantee every time your training set is of high quality, right? So when we talk about the performance of particular learning algorithm, right, we need to use some probability language. So the most common used language is like epsilon delta language, although the epsilon delta is different from that in calculus, right? It's saying that, okay, with probability at least some level, right, 1 minus delta, your learned algorithm, learned hypothesis will have true error less than epsilon, right? You cannot say, okay, you definitely can get your learned hypothesis with any training set with true error less than epsilon. That's the key idea of pack learning. And let us just review the sample complexity bound when we discuss about the consistent learner, right? Namely, we assume your hypothesis space is rich enough and the learning algorithm is powerful enough. Every time on whatever training set, you're going to return a consistent hypothesis to all the training examples. And then we claim that if the number of training examples for a consistent learner is bigger than this guy, then with high chance, at least 1 minus delta, the learned hypothesis by your consistent learner will have true error less than epsilon. So of course, this sample complexity bound is determined by the designated level of the confidence and error, right? True error. Any questions so far? We actually have derived, I'm sure how we get this, right? But here we just want to refresh our mind and look at the previous conclusion we have derived together, right? So any question so far in recalling those kind of stuffs we discussed before? Okay, great. Assume everybody is on the same page, right? So to derive this conclusion, to derive this sample complexity, actually we're based on two key assumptions, right? The first assumption is that the training and test examples are assumed to come from the same data distribution, which is pretty reasonable, right? We can always assume, okay, our training data and test data come from the same data source, right? we use training data to train, and then the test examples will be sampled from the same underlying distribution, although highly complicated. But the second assumption is a little bit problematic, because we're assuming we have a consistent learner, meaning that for any concept target function, there is some function in the hypothesis space that is consistent with the training set, right? So you can imagine there can be some gap between your learned hypothesis and the target function in the concept. Right? So the more training examples involved, right? Because every time you're gonna find a hypothesis which is fully consistent with all the training examples, right? Meaning that when you increase the training set, you kind of like make your learned hypothesis and target function get closer and closer, right? And you can increase M to be number of training examples to be arbitrarily large. Then what kind of hypothesis space can ensure this? What kind of hypothesis space can ensure that no matter how large your training set is, you can find a hypothesis which is fully consistent with all the training examples? Any thought?
So you're asking, like, what is a hypothesis space for which, what exactly?
Yeah, what is hypothesis space that can guarantee that, okay, no matter how large your training set is, I can always find a hypothesis which can correctly predict all the training examples.
I think I might be a little bit like, I'm not sure exactly how to describe a hypothesis space, but if if the pattern that you're looking for is really simple, like, or, say it's, maybe it's linear, I guess, then you can say, like, you can always find something that matches.
Yeah. But you can imagine the target function or the concept is some point in the candidate space, right? Your hypothesis space is a set of points of those candidates, a set of candidates. Right? So actually, we're making a strong assumption in the consistent learning setting that for any set of training examples, I can always find a hypothesis which gives zero training error.
I see. So a hypothesis space is like what is essentially a subset of like points that we're going to be able to predict, right? It's kind of like the types of patterns that we can think about with our model, right?
Yeah. But compared to the target concept, right? So what kind of hypothesis can ensure that you can find a hypothesis which can be arbitrarily close to any target function?
So are we looking at a function definition here? Like what kind of a function would actually give a training error zero? Or
Yes.
can we do a collection of functions, like one function identifies correctly one training example, and the collection of those, collection of all those, how many training examples are there, those functions will be the hypothesis.
Oh no, has nothing to do with. I mean, after the training example, what kind of function you get? Actually, just the pre-assumption of the candidate set of functions you're gonna search over. This is called hypothesis space, right? So
It can be infinite, right? Then
it can be infinite, of course.
yeah.
You can imagine, like, actually, we're assuming that, okay, no matter how large your training set, we can find a hypothesis which can predict exact the same as the target function for every training example. actually the size of training set can be viewed as kind of reflection of the gap between the target function and your learned hypothesis. Right? So the more the prediction, the more of the number of the predictions consistent between the two, the closer the two functions, right? So actually, this implies that, okay, no matter what kind of target function you have, I can find a hypothesis which can be arbitrarily close to a target function. This actually implies that your target functions must be inside the hypothesis space.
I see. So like it's assuming that you've chosen the hypothesis space correctly, essentially, right? That you have a hypothesis space that allows you to actually solve the problem, like find.
Yeah. You can view this correctly. I would say large enough to cover all possible target functions. Only in this way, like you can get arbitrarily close to any target function. Otherwise, suppose your target function is outside, right? Even the closest hypothesis space, there can be some significant gap, meaning that at least one training example, your hypothesis space will make wrong prediction, will make inconsistent prediction. That doesn't satisfy our assumption of consistent learning. So this is a key assumption. We assume that the learning algorithm can find consistent hypothesis. In any case, it means that, okay, your concept class, the family of all target functions must be belong or a subset of whole hypothesis space, right? The hypothesis space is large enough. However, this is not always true in practice, right? In many learning problems, you actually don't know which particular family your target function belongs to, right? If you want to predict tomorrow the stock price is gonna increase or decrease, right? You don't know if this mapping is underlying function is a linear function, is a quadratic function, is a third order polynomial function, or it contains sine, cosine, logarithm. You don't know actually. In many cases, you cannot exactly define the type or the range of the target function. And as a consequence, it's really impossible to ensure that the whole hypothesis space you're choosing kind of like cover all possible target functions. This more realistic setting is called agnostic learning. So basically, we're trying to learn a concept or target function f using some designated hypothesis space, big H, right? But this target function f does not necessarily belong to H, like here. The target function can be outside of the space. In more general case, we can assume, okay, the concept class kind of overlap with hypothesis space, but does not necessarily be contained in this hypothesis space. Or in even worst case, the whole concept class can be distant from the hypothesis space. So this setting is called agnostic learning. And we are curious about that. On the agnostic learning setting, can we still say something about the sample complexity? Can we still give some estimate or the upper bound of the generalization error given the training error? So any question regarding the definition or the concept of the agnostic learning? Okay.
Actually, sorry. So agnostic learning is talking about like when you're trying to learn something and your hypothesis doesn't contain the entire concept space, basically.
Does not necessarily contain the entire concept class. meaning that you might have zero training error.
I see. So it's learning without the assumption that we've had so far, essentially.
Yes, yes,
Okay.
exactly.
And so then we're gonna like, okay, so then we can't use the Occam's razor principle from earlier. Like we can't say any of that because we don't know whether or not our assumptions hold.
Yeah, yeah. But you see that we can also derive some sample complexity bound, derive some generalization error bound, which can reflect Occam's razor as well.
Gotcha. Okay, thank you.
Okay. Any other?
So which one of these, under these conditions where F is not an element of H, which assumption is that breaking? Is this a breaking that consistent assumption?
Yes, it's breaking consistent assumption.
Okay.
Yeah, previously we assume, okay, in whatever case, whatever data set, like, you always find a hypothesis which gives zero training error.
Mm-hmm.
As we just discussed, right, that actually implies you can find an arbitrary close hypothesis to the target function, which further show that actually your target function must belong to the hypothesis space. Otherwise, you cannot do that.
Okay, I see.
But unfortunately, this is too unrealistic, too ideal, right? So we consider a more realistic case where we acknowledge that it could be possible that your target function is outside of the hypothesis space. Even you find the best hypothesis in this hypothesis space, there can still be some significant gap between your learned hypothesis and the target function. Okay, so under agnostic learning, right, the key difference from the previous consistent learning we discussed, right, is that we're gonna no longer guarantee the training error is zero. We need to acknowledge that we might have non-zero training. So this is a key difference, right? So in our previous ideal case or polite case, right, we always assume on the consistent learning, we always assume the training error is zero, right? So that we can derive a bunch of stuffs, right? When the number of training examples is at least blah blah blah, then we guarantee our learned hypothesis have a true error less than some epsilon under some probability level, right? But here in the agnostic learning, right, we don't have that strong assumption. We can assume that the training error can be non-zero.
Is the gradient descent that we implemented an example of agnostic learning where like we're trying to fit it as best as possible, but we're not kind of expecting to fit every training example?
Yeah, that's a great question. Yeah, actually, most models we have seen or we have used is actually agnostic learning, because we cannot guarantee your training error is zero.
Mm-hmm. And also, like anytime we have noise in our training examples, like that kind of has to be agnostic, right? I guess. Well, we can't have training error of zero necessarily.
Yeah, you're right. But here we do not consider the effect of noises.
Okay.
Here we just assume, okay, all the training data and test data come from the same data distribution. They're yet corrupted by some noises.
Got you. Okay. Yeah. So we assume that we're at least sampling correctly, right? Without noise.
We're sampling correctly. Our training data is okay. It's fine. It's totally fine, right?
Mm-hmm. And if we remove that assumption that there isn't noise, that doesn't make it agnostic. That's something else, basically.
You can say it's a kind of agnostic learning, agnostic corruption. Yeah, but if you want to build some theoretical things upon that, we need to talk about other topics. It's not something we focus on here.
Gotcha. It's not directly related. Got it.
No, it's not there. Okay, great. Any other question regarding the setting of agnostic learning? Okay, great. So yeah, so just keep in mind, right? Agnostic learning is the closest to the practice where we no longer assume your training error is zero. It's actually rarely it's very hard to satisfy in practice. However, that does not mean we're not gonna try to learn a hypothesis with small training error. Instead, it's similar to the consistent learning behavior. We still want to find a classifier or the hypothesis in the hypothesis space that has training error as small as possible. The rationale is that, okay, although our target function is outside the hypothesis space, right? By reducing the training error, right, we can find a hypothesis which to be as close to the target function as possible, so that when we apply our learned hypothesis to predict future unseen examples, our performance won't be too bad, right? Will be good as well. That's the rationale. So even under agnostic learning setting, like, we're still trying our best to reduce the training error. And then what is the definition of training error? Like, here we just consider the binary classification case, right? So let us just review the definition of the training error, which is just the proportion of misclassified training examples, right? Suppose we have m training examples. We just look at, for every training example, if it is correct to predict our learned hypothesis or not, right? It will just count how many of them are incorrectly predicted and divided by the total number of training examples, we get our training error. That is the fraction of training examples misclassified. So given the training error, right, under agnostic learning analysis, we want some guarantee. A hypothesis with small training error will have a good accuracy on unseen examples. In other words, we won't find a guarantee based upon training error to claim a small generalization error or small true error. That's the key task of agnostic learning theory. And we notice that we have non-zero training error, right? But based upon non-zero training error, we want to give some estimate or upper bound about the true error. Then I can claim that, okay, this true error is determined by the training error is determined by other factors. So as long as we can keep an eye on setting of those factors, we can ensure our generalization error is good. So what's the definition of the generalization error? Right here, I want to review it again, because later we'll say how can we derive the relationship, namely the training error and the generalization error. So the generalization error is defined as a probability that for arbitrary example that is sampled from data distribution, the prediction made by the hypothesis is incorrect. Namely, the prediction of H is different from the prediction of the target function F. So it is a constant, it's a probability, right? And by the on the contrary, the training error is essentially a random variable. Why? Did anyone give me some hint why this training error is essentially a random variable?
Because it will depend on the number of training examples.
It's actually not number of training examples. It depends on the training example, right? Because the training data is sampled from data distribution, right?
Yeah.
So the training data is essentially a random variable. Yeah, it's a collection of samples, but they are random variables as well. So the training error is essentially a function of the training set, right? The training set is a random variable. Of course, the training error is a random variable as well. We'll, given this H and F, right, we'll resample the training set and test it. It might be another value. So mathematically speaking, in the theory about agnostic learning, we want to use the training error, this random variable, to derive some guarantee or bound about the true error, which is not random variable, it's just some fixed unknown constant. Okay. But how can we get this? How can we derive this bound? We're going to use the so-called tail bounds for analysis. So what are tail bounds? They're a set of probability inequalities. I'm pretty much sure every one of you has seen many. Right? And those tail bounds were originally proposed to quantify the probability that a random variable get far away from its mean. In your statistics course, a probability course, we know that okay, all the random variables they have more probability to stay around their means. Right? The farther away the random variable from its mean, the smaller the probability of such kind of events. So tail bounds just give you an estimate or upper bound of such kind of probability. Let's see a few commonly used examples. So the first example is called Markov inequality. I almost say this Markov inequality in every statistical book and the probability book. So Markov inequality bounds the probability that a non-negative random variable exceeds some fixed value. Say, suppose I have a non-negative random variable x, then the probability of x bigger than or equal to a is upper bounded by the expectation of x over a. So you can imagine that if a is very large, and the upper bound will be very small. Upper bound is very small. That means okay, the chance that x gets a away from the origin is very low. The Markov inequality is pretty, it's pretty rough, right? A more refined, a more elegant inequality is called Chebyshev inequality. It actually bounds the probability that a random variable differs from its mean by more than a fixed number of standard deviations. Specifically, we can consider arbitrary random variables. It can be positive, it can be negative. Right? So Chebyshev inequality tells us that, okay, the chance that x gets k standard deviations away from its mean is less than or equal to 1 over p squared. So mu is the variable, is the expectation or mean of x, and sigma is actually standard deviation. It just tells us, okay, the probability that x gets k standard deviation away is reduced to p squared. It reduces very fast, right? These are two commonly introduced probability inequality in textbooks, but those are not applicable to our problem, because in our problem we do not want to bound a random variable, a single random variable. Essentially, we want to bound the average of a set of random variables. Why? Because later we'll see the training error essentially is viewed as an average of m random variables, random binary variables. M is number of examples. We'll look into that later. But first, let us look at the probability bounds we're going to use in our advanced learning setting, which is called Hopkins inequality. So what is Hopkins inequality? It upper bounds on how much the average of a set of ID random variables differs from its expected value. So here, P bar is an average of n independent, identically distributed random variables. So x1, x2 to xm, we just do the average, we get P bar. And P here is the expectation of each random variable. Of course, they are the same because they are ID, right? And also, P is also the expectation of this average. If it takes expectation of the average of set ID random variables, the expectation is the same as individual random variables. So if you look at this Hopkins inequality again, right, it says that the chance that your average random variable is epsilon distance away from the true expectation. Is less than or equal to this exponential factor. So the power is -2 m. M is the number of the variables to enrich in p bar, and epsilon squared. So what does this Hopkins inequality reflect? It actually reflects that if you average a set of ID random variables, the chance that it gets far away from the mean is even low. Right? You can see that it's upper bounded by some exponential negative power. It's very, very small. So when we increase the number of the variables to be enriched, like, namely m, the chance that the average random variable gets the same distance away from its mean decreases exponentially fast, exponentially to m. If you look at how this probability decays along with distance epsilon, you will see that it decays even faster. You first take epsilon square and take exponential and take minus one. So it actually decays square exponential away, even faster. It means that, okay, if you have enough number of training examples, if you have enough number of the IID random variables to average them, this right-hand side is close to 0, meaning that, okay, you're almost always have your average random variable value to be close to the true mean. Okay, any question in regarding the understanding of this Hopkins inequality? Okay, great. So now how can we apply this Hopkins inequality in our agnostic learning setting, right? So first, we can view this p bar, which is an average of m ID random variables. This is essentially an estimation of the mean, right? If you want to calculate the expectation or the mean of some kind of random experiments outcome, which is random variable, right? So do it multiple times, right? And then just average the outcomes together. This is the common way to estimate the mean of those random variables, right? So actually p bar represents the empirical mean, and it is a random variable. Why? Because it's a function. It's the average of m random variables. It is a random variable for sure. It's computed from m independent trials. And p itself is a true mean because it is expectation of random variable. It is expectation of this mean. It's the expectation of this average. So the Hopkins inequality tells us that the empirical mean or the estimate of the mean will not be too far from the true mean if there are many examples. As we mentioned, if m is large enough, right, and given the fixed epsilon, m is large enough, this value can be very, very close to 0, right? Meaning that, okay, you almost have an empirical mean to be the same as the true mean. So now let us look at the definition of the training error and the true error. So as we mentioned, training error is defined as the number of incorrectly predicted training examples over the total number of training examples. Right? So how can we calculate number of incorrect predictions? Right? Which is essentially a summation over m binary variables. We just look at every training example and say if the prediction is correct or not. Right? This indicator actually is a binary variable. And this is a binary random variable. Why? Because each training example xi is sampled from some underlying data distribution. So xi is a random variable. So this indicator function is a function of random variable. So it is random variable. And their IID. Why? Because all the training examples are assumed to be sampled from IID. Now we can see the error. the training error on the training set S, right, is essentially an average of n independent, identically distributed random variables. Then, what is the expectation of the training error, or what is the expectation of each binary indicator variable it averages? An idea? Any thought? We need to review our knowledge about binary variables, right? If you want to take a mean of a binary variable, what is its mean, or what is expectation?
Isn't it the integral of, it's the probability times the value of each random variable summed up? So like, I guess over an integral.
Yes, it's an integral. But for binary random variables, we know that it either takes 1 or 0, right?
Right.
So what is the expectation? Or what is its integral?
Wouldn't it then just be the so okay, so 1 means that we've correctly predicted, right? So just be then wouldn't it just be the expectation would just be the sum of the probabilities of the correct predictions?
And the probability times the probability of incorrect prediction times 0, right?
Right, but that'll all just go to 0.
Yes. So that actually is an important fact, right? So the expectation of a binary variable is essentially the probability the variable is 1.
Yes. Okay, I see.
Right. So if we look at the expectation or the mean of each binary variable here, right, in the training error, which is essentially the probability that this indicator function is 1, meaning that the probability your prediction is wrong. Right? The probability your prediction function, your prediction is wrong, is actually the true error. Right? This is our definition of true error, or the generalization error. That is, for arbitrary example X, sample from data distribution, your probability, the prediction is wrong. Right? So now we can draw the connection between the true error and the training error. Essentially, the expectation of the true error of the training error is the true error, and the expectation of each binary indicator is the true error. So now we can say P bar here is essentially an empirical mean or empirical estimation of the true error, which is a training error, right? And P here corresponds to the generalization error. So naturally, we want to ask, right, what is the probability that the true error is more than epsilon away from the empirical error or the training error? To get this answer, we just apply the Hopkins inequality. So here, P bar is replaced by our empirical error or the training error, because this is just an average of n IID binary indicator. And here, P is replaced by the true error, because it is the mean of each binary indicator averaged in the empirical error, or the mean of whole empirical error. Remember, empirical error or the training error is just one variable. So then we can just apply Hopkins inequality. We can claim that, okay, the true error epsilon away from the training error is upper bounded by this exponential factor e to the power of -2 times the number of training examples times epsilon squared. So this is our first conclusion, right, made from the agnostic learning. By directly applying the Hopkins inequality, we claim that for a single hypothesis H, the probability that H has a true error that is more than epsilon away from the training error is bounded above by this exponential factor. Any questions so far? Okay, great. But this is not the end, right? Actually, when we conduct learning procedure, before we do the learning, right, we do not know which particular hypothesis is going to be chosen as our learned hypothesis. As in a consistent learning case, right, we want to bound the probability of some bad event. Namely, okay, I find some hypothesis by taking my best efforts, but the hypothesis is still bad, meaning that the learned hypothesis is still epsilon away from the training error. So I want to bound such kind of probability. How can we bound that probability? We cannot just use, okay, for detailed specific hypothesis, what is such kind of bound? Well, actually, we need to look at the probability there exists such a bad hypothesis whose true error is epsilon away from the training error. What is that? What is the bound for such kind of probability? And note that there is a subtle difference here. So here, we just suppose this hypothesis is given and in front of you, right? And I can claim, okay, the true error, the probability of the true error is epsilon away from the training error is bounded by this, right? But here we're looking at the property of the entire hypothesis space. We're saying, okay, there exists such a bad hypothesis whose true error is epsilon away from the training error. What is the bound of such kind of probability? And then we can use this bound to claim the worst case where our learning algorithm will behave. That is, in the case that our learning algorithm pick up such bad hypothesis. The problem, because how can we derive this bound? Right? So actually, we can use the same trick we have used before. Right? In the consistent learning behavior, when we talk about the event that there exists some hypothesis, this event happened, right? This existent event can be decomposed as a union of set events, where each individual event will be each one its true error is more than epsilon away from its training error, or H2 its true error is more than epsilon away from its training error, blah 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 until, right? So this event is essentially a union of the following events. So when we calculate the probability of a union of set events, it is upper bounded by the summation of the probability of each individual events, right? Listed here. And we know that for each individual specific event, this probability is upper bounded by the exponential factor, right? So just as all the bounds together, we get the upper bound of this existent event. So now we can think that, okay, there exists a hypothesis in a hypothesis space such that its true error is epsilon away from the training error is less than or equal to the size of the hypothesis space times e to the power of -2 and epsilon squared. this is an analogy, right? Analogy to the consistent learner case we discussed, right? So in the consistent learning case, we assume that every time we are gonna find a hypothesis which is consistent with all the training examples, right? But we don't want some bad event to happen. That bad event is defined as okay, your hypothesis is consistent, yet the generalization error of learned hypothesis is still bigger than epsilon, right? This is defined as a bad event. So we derived some bound for the probability of that bad event to happen. But here, we define the bad event as, okay, there exists some hypothesis whose true error is epsilon away from the true error. We want to know what is the maximum chance of that bad event happening. And we use the same trick to derive everything. Okay, any questions so far in understanding these inequalities? Okay, seems everyone is fine with that. Okay, I'm just worried, but you might feel confused about that, but it's okay. It looks like everybody adapts to the computational learning theory very quickly. So now, of course, we don't want this bad event to happen. Right? We want to control the chance of this bad event to be under some particular level. Right? Say I want this bad event to happen, the chance to be less than delta. How can we ensure that? We just solve the inequality that the upper bound of this bad event is less than delta. And then we just solve this inequality in terms of number of training examples. We get our sample complexity bound for the agnostic level. First, intuitively, if you want to reduce the chance that okay, your learned hypothesis is epsilon away from the the true error of the learned hypothesis is epsilon away from the its training error, is that you just increase the number of training examples. Right? Why? Because the more the training examples you use, right, the training error is closer to the true error. Right? Because remember, training error is an estimate or empirical estimate of the true error. Right? The more samples you're going to use, the more accurate you're going to estimate. Right? So intuitively, yes, the more training examples you involve, the less likely that your true error is quite different from the training error. But how can we quantify the number of training examples we want? Right? So this is how we derive this sample complexity bound. Namely, as long as number of training example is bigger than this guy, of course, this guy is determined by the designated level epsilon and the confidence level delta, and also the size of hypothesis space. If m is bigger than this guy, then we can ensure that with high chance your true error will be epsilon, will be within epsilon distance from the training error. Okay. So now let me summarize, right? And look for interpretation of the sample complexity bound we have derived so far. It just says that, okay, an agnostic learner makes no commitment whether our target function f is in the hypothesis space H. But it can still guarantee with probability 1 minus delta that the true error is not off by more than epsilon away from the training error if the number of training examples is enough large. But how large is it? It should be at least no less than this number. Of course, this lower bound of the sample size is determined by your epsilon, the delta, and the size of hypothesis space. But here we should be aware of a significant difference from the consistent learning behavior. In a consistent learning setting, right, our conclusion, the epsilon was introduced the level of the absolute level of the true error, meaning that okay, when the number of training examples is bigger than something, okay, I can guarantee with high chance your true error is less than epsilon. But here, we're not talking about the true level is less than epsilon. We're just talking about the true level, the true error is not epsilon away from the training error. Why? Because the training error is not zero. Right? So epsilon here characterize the difference between the generalization and the training error. How much worse will the classifier be in the future than it is in the training time? And H, of course, here the log size of H indicates the complexity of the hypothesis space, right? It justifies again the Occam's razor principle. So given the same epsilon delta, the smaller the size hypothesis space, the smaller number of training examples you would need to get the same distance between or difference between the true error and the training error. So you can see we actually obtain kind of very similar structure as the sample complexity bound we derive for consistent learning. But just keep in mind the difference of epsilon, the meaning of epsilon here. Epsilon does not represent the absolute level of the true error in agnostic learning. It just represents the difference between the true error and the training. Okay, any questions so far?
What's the difference between the epsilon in this case and the epsilon that we used in pack learnability? Can you explain that again?
Yeah. So if we look at the consistent learning case we discussed before, right? It talks about, okay, if the number of training examples is bigger than some guy, right? The some lower bound, then with high chance, at least 1 minus delta, the true error is strictly less than epsilon. So let me write it down. The true error.
That was before, right? That's the definition in pack learnability.
That's the user for definition of pack learning. But here we talk about the consistent learning behavior, the sample complexity bound we derived previously.
Okay.
Right? We mentioned some bound like m is bigger than something, then we claim that it has probability at least 1 minus delta. The true error is less than epsilon. Right? In that case, epsilon indicates the level, the absolute level of the true error, right?
Okay.
But here, in the agnostic learning, epsilon just represents the offset from training error to the true error. It's just difference between the training error and true error. In other words, what we can see is that, okay, when the number of training examples is bigger than this guy, we claim that with high chance, at least 1 minus delta, the difference between the true error and the training error is less than epsilon. If we want to get to the absolute level of the true error, we're going to plus the training error in the case of agnostic learning. Do you see the difference?
Yeah. So the true error definition across consistent and agnostic learning is same, but the epsilon definition is different. Is that
Yes.
Understanding correct?
Yes, exactly. The true error and training error are defined exactly the same as the previous. We don't change any definition of training error and true error. But here, the epsilon was used for another definition. It's not used to indicate the absolute level of the true error.
So is that is this correct? We can assume that this epsilon in agnostic learning can be smaller than true error, or we can't put any equality or inequality on the epsilon between
Yeah,
this.
epsilon here has nothing to do with the true error, the absolute level of true error. Like epsilon can take 0.05, right? And your true error could be 0.1. It's possible.
Okay.
Because epsilon indicates the true error subtracted by the training error.
Okay, correct.
This is epsilon. If you want to get the true error, you actually have epsilon plus the training error. Does it make sense?
Yeah.
So actually your true error, your generalization error is determined by two facts. One is epsilon, the difference from the training error. Second is the training error level itself. Of course, the smaller the training error you get, the smaller the true error. At the same time, you need to ensure, okay, their difference is small.
Yeah.
Okay, any other question? Oh, great. I'm happy that everybody can differentiate the difference, right? I mean, differentiate the result of agnostic learning and consistent learning. But the only difference lies from the usage of this epsilon. Epsilon is in agnostic learning setting is used to characterize the difference between training and the true error. So, and we can further switch that epsilon and m, right? Because epsilon represents difference between the true error and the training error. Right? If we move m here and move epsilon here, right, we get another bound which is called generalization error bound. We see that, okay, if we have m examples, we fix m examples, then we still have a high probability to claim that this epsilon, namely the difference between the true error and the training error, is upper bounded by this. This is just derived by switching epsilon m and take square root on the right hand side. This reflects better, more clear, the relationship between the true error and the training error. This inequality tells us that with high chance, the generalization error is upper bounded by the training error plus this term. So now we can say from this sample complexity bound, right, from this generalization error bound, we can say, or what kind of actions we can take to reduce the generalization error. First, we can reduce the training error. Because if you move the training error on the right hand side, right, so you got this error d less than or equal to this guy plus the training error, right? So if you want your true error to be small, right, first you need to ensure your training error to be small. And secondly, you want to make this bound to be as small as possible. Right? How can you reduce this upper bound? You can increase the size of training data, right? It's very intuitive, right? We know that when we increase the size of training data, you have more training examples, you're gonna get better performance in predicting future examples. Right? And also, you reduce the size of hypothesis space. This, again, justifies the Occam's razor principle. the smaller, the simpler hypothesis space you use, the tighter the generalization error bound you get. Right? I mean that your generalization error is closer to the training error. And thirdly, you can see that the more confidence you want, right? Because it's a probability statement, probability inequality. We say this bound satisfied with high chance, meaning at least 1 minus delta probability. Right? So the larger confidence you want, right? Meaning that the smaller delta, then the loser bound. So here's what we get from this agnostic learning, right? We got the sample complexity, right? Actually reflects the same kind of insights as the consistent learning setting, right? We also get the generalization error bound. You see that the generalization error bound provides us the K insight in developing the max margin classifiers, namely support vector machines. And you will see that in support vector machines, we're assuming that, okay, the training error are all at the same level, but by reducing this upper bound term, right, we can effectively reduce the generalization error. Right? How can we reduce this upper bound term? We find the linear classifiers who has the largest margin. When you maximize the margin, when you find the largest margin, you're actually effectively reducing the complexity of hypothesis space. Of course, in that case, the complexity of hypothesis space is no longer simply represented by log size hypothesis space, because the linear classifiers, the hypothesis space is infinite. Right? We cannot just take logarithm of their size. Okay, so far regarding the computational learning theory, right? In addition to those basic concepts like pack learning, like epsilon delta language, right? We introduced two cases. One is consistent learning, the other is agnostic learning, right? Consistent learning assumes that, okay, we're gonna always find a hypothesis which gives zero training error, right? And then we claim that when the number of training examples is bigger than this, and with high chance 1 minus delta, the true error is strictly less than epsilon. So epsilon in the consistent learning case indicates the absolute level of the true error. But for agnostic learning, we no longer assume the training error is zero. Then what we can claim is that, okay, when the number of training examples is bigger than this, then the true error will have large chance to be epsilon, to be inside the epsilon distance from the training error. So epsilon is actually the offside, or difference from the true error and the training error. Any questions so far? Is everyone satisfied? Is everyone okay? Happy with this? Or is it too simple? I'm trying to slow down a little bit, right, to ensure everyone is on the same page, because our later discussion about support vector machines and large margin classifiers, all kinds of things are based upon the observation of this. Okay, that's great. Right? So far it looks like we got like very perfect example, very elegant result, right? We justify Occam's razor twice or 3 times. Right? That looks good. But can we solve everything? The answer obviously is no. Why? Because in both cases, in both sample complexity and the generalization error bound, right? We assume that we can calculate this log size of the hypothesis space. Meaning that only when your hypothesis space is finite, you got meaningful and reasonable bound of samples, bound of sample size, or bound of the generalization error. However, even for linear classifiers, perhaps the most simple machine learning models, the hypothesis space is infinite. If it's infinite, you can no longer use those ones to evaluate the performance of a learning algorithm or the number of training examples we need to get to reach particular level of accuracy. Okay? That stimulates the invention of other measurements to measure the complexity or the expressiveness of hypothesis space. So my first question, just to incur your thinking, right, is for two hypothesis spaces, right, both are infinite. Do they have like difference in terms of expressiveness?
I'm not sure what you mean by expressiveness, but probably.
Expressiveness meaning, okay, how can I represent these things? How complex classification result I can give, whatever. Like we assume, okay, I have an A and B, right? A is both A and B are infinite hypothesis space. Right? What I want to ask is that can we compare their expressiveness? Like if A and B are both finite, well, it is quite easy. Right? Just look at the size, right? So if A only contains 3 possible functions and B contains 30, right? We can claim that, okay, B is more expressive because I have more labeling functions. Right? Or can generate more diverse labels. But what about infinite hypothesis space?
Could you give like an example of an expressive one and a less expressive one or something like that? Kind of describe like
yeah, of course.
comparison.
So we just look at this example, right? So I'm gonna give like 3 infinite hypothesis spaces, right? One is rectangles, the other is 17 size convex polygons, and 3 is general convex polygons. So you can imagine for each particular polygon, right? Remember, rectangle is also polygon, right? So we can construct classifier where for all examples inside of the polygon, we classify as positive, outside classify as negative. So I want to ask for these 3 types of classifiers or hypothesis spaces, which one do you think is more expressive or more complex or more capable?
I see. So it looks like the pattern is like left to right, you get more complex, right? Because a general convex polygon, there's a lot more stuff you can fit in there, even though they're both infinite, right? Or both continuous. Question on that, like a rectangle, I think you could probably define it as like 2 integers, right? Where, you know, it's like the width and height, right?
And it's not necessarily integers. It could be real values.
Right, real values, sure. So that's like 2 attributes, you could say. And then when you go to 17-sided convex polygons, right, you have a lot more attributes. Is that kind of how we're looking at expressiveness? Like
yes,
how
yes.
many?
Yeah, I just want to get your intuition on that. Yeah, you're right. They also give some analysis.
Gotcha. Okay, that makes sense.
Yeah. So we can see that even for infinite hypothesis space, right, both sets have an infinite uncountable set of candidates, right? You can still feel the difference in terms of expressiveness, capability to give labels, give predictions, whatever. So obviously, for infinite hypothesis spaces, we should have some measurement which can reflect their expressiveness or capacity. Another example is the linear threshold function, namely linear classifiers, versus a combination of linear classifiers. A combination of linear classifier can be viewed as a weighted combination of linear classifiers, like what you did in the A-levels, right? So obviously, both are infinite hypothesis spaces, but single linear classifiers is less expressive than a combination of them. Why? Because any single linear threshold function can be viewed as a special case of combination. Like the component is just one. And in addition to single linear threshold functions, I can have a combination of two linear functions, combination of three linear functions, four, and so on. Then you can become the piecewise nonlinear functions. Right? So in the latter case, obviously, a combination of linear threshold units can be much more expressive than a linear threshold function. Then the question is that, how can we come out a new measure that can reflect the difference of the expressiveness of those hypothesis spaces when they are infinite? Let us discuss about that problem in the next lecture. Thanks. We'll stop here.